Welcome back everyone to this lecture on the Perceptron Model. To begin understanding deep learning, we're going to start by actually building up our model abstractions. We're going to begin by exploring what real single biological neurons look like. Then we'll model those mathematically as a single perceptron, see how we can group together perceptrons, or artificial neurons, to build out a multi-layer perceptron model, and then see how that expands to a deep learning neural network framework. So as we learn more about complex models, we'll also then introduce some key mathematical concepts to the actual mathematical functionality of those neurons, and that is things like activation functions, gradient descent, and backpropagation. But for right now, we're going to focus on just building out that single perceptron model based off a real biological neuron. So, if the whole idea behind deep learning is to have computers artificially mimic biological and natural intelligence, it's probably a good idea that we should build a general understanding of how biological neurons work. So here we can see some real stained neurons in a cerebral cortex. And basically what we're going to attempt to do is check out the way these biological neurons work and see if we can develop a simplified abstraction off these real neurons. So here's an illustration of biological neurons, and you can see that there is a lot going on, and don't worry, this isn't a biology class. And the main things we're going to focus on is just the neuron itself. So the main things to see here is that there's some sort of nucleus or center to this neuron, there's the cell body, and it looks like we have both inputs and outputs or axons spreading out from this nucleus. So let's take this illustration of a biological neuron, and what we're going to do is we're going to really simplify this. And we're going to simplify it so much that I will actually create my own illustration. And I'm definitely not an artist, so this is an extremely kind of rough illustration, but don't worry, you'll see why I drew it like this later on in this lecture. But the main thing we want to focus off the biological components are the dendrites, and we can think of those as input going into the main nucleus of this neuron, and then the axon, which is some sort of output. Now, again, this isn't 100% biologically correct, but this feeds into our perceptron model. Basically, we're going to think of neurons biologically as accepting some sort of input signal, and the input signal can come from a variety of sources, and then we'll do some sort of calculation in the nucleus, or something happens in the nucleus of this neuron, and then it outputs as a single output axon, and that can then lead over to another nucleus as the dendrite to another neuron. Now, how do we take this very simplified biological neuron model and convert it into a mathematical model? This is where the idea of the perceptron comes in. A perceptron was a form of neural network introduced all the way back in 1958 by Frank Rosenblatt. And amazingly, even back then in the 1950s, he saw huge potential, stating, quote, "A perceptron may eventually be able to learn, make decisions, and translate languages." And if you've ever used something like Google Translate actually uses a neural network as its main way of converting from one language to another. And Frank Rosenblatt actually saw the perceptron as one of the main base units to building out that sort of technology. And he thought of this all the way back in the late 1950s. However, about a decade later, in the late 1960s, two researchers, Marvin Minsky and Seymour Papert, they published a book labeled Perceptrons. And it suggested that there were actually severe limitations to what perceptrons would be able to do. And a big part of that limitation was the actual computational power necessary to work with multi-layer perceptron models. So back in the late 1960s, there wasn't really enough computational power to actually make full use of the idea of the perceptron mathematical model. And this publication of this book actually marks the beginning of what's known as the AI winter, where very little funding went into research in artificial intelligence and neural networks in the 1970s. So that's why, even though this idea was spawned in the late 1950s, it's taken up to the modern age to actually fully implement neural networks. Now, fortunately for us, we already now live in the present and we know the amazing power of neural networks, which all really stem from this simple perceptron model that was created all the way back in 1958. So let's go ahead and head back and convert that simple biological neuron model into the perceptron model, and then go through a simple example of how a perceptron model works. So recall, we have a very simplified biological neuron model. So this is the biological neuron modeled in a very simple fashion where we have incoming dendrites, then some sort of center nucleus, and a single output to the axon. So what we're going to do is instead, we're going to replace these biological units with some mathematical ones. So what we're going to do is we're going to define some set of inputs going into this single point, which we'll call the neuron, and then has that single output. So let's go ahead and work through a simple example of how the simple perceptron model actually works. What we're going to do is we're going to imagine essentially two data points, x1 and x2. So these two variables, x1 and x2, are going into as input into this perceptron. And you can imagine that inside this perceptron, that neuron is going to have some sort of function. So it's going to have some sort of functionality and perform something on those inputs of x. And it's going to then output some y. So we have some function inside the neuron, takes in these x values, performs something on them, and then outputs y. So if f of x, that function, is just a sum, then y is equal to x1 plus x2. And this is a very, very simplified perceptron model. Later on, we'll expand on this with activation functions. But for right now, this is just showing you how we can go from a biological neuron to a perceptron model. So we have these inputs, x1 and x2. We push them through some sort of function of x, and then we output some y. So realistically, we would want to be able to adjust some parameter in order for the perceptron to learn. Right now, there's no real way for the perceptron to adjust its ability to learn to kind of correct the output of y. So what we can do is we can add in adjustable weights that will multiply against these inputs of x. So what we're going to say here is that we'll take in each input of x and apply it to its own weight. And then we can adjust that weight as necessary in order to get the correct value of y, or the expected value of y that maybe we're performing some sort of supervised learning on. So maybe we're trying to solve a regression task where y is the actual continuous label we're trying to predict. Or maybe we're doing classification and y is a category. But the most important part here is we're going to need to be able to take this perceptron model and adjust it somehow in order to get the correct value of y. And one way we can do this is by applying a weight to each input, and then we can adjust the weight. So we'll label these weights corresponding to their inputs as w1 for x1 and w2 for x2, which means if our function, still simplified as just an addition, we'll say y is equal to x1 times w1 plus x2 times w2. Now we could update the weights in order to affect the output y. But what happens if x input is actually 0? That means no matter what you do to the weight, that actually won't change anything. So to fix that problem, we could add in a bias term b to the inputs. So regardless if x1 is 0 or x2 is 0, which means that when you multiply it by a weight, it'll always end up being 0 regardless of how you update the weight. What we can do is we can add in a bias term b to the inputs. So we essentially assign this neuron its own particular bias, so that the inputs end up not just getting multiplied by a weight, but having a bias added to them. And keep in mind, the weights can be positive or negative, and the biases can also be positive or negative. A good way to think about the bias is that the multiplication or the product of x1 times w1, or the input times its weight, has to overcome the bias value in order to start having an effect on the output of y. So here, for this very simple example, we end up approximating the output of y to be equal to x1 times w1 plus b plus x2 times w2 plus b. And this is just a very simple summation that's happening inside the neuron. Later on, we'll talk about more realistic activation functions that you'll have in typical networks. Keep in mind, we can expand this to a generalization for a variety of inputs all the way to some input n. And so now we've been able to see how we can model a biological neuron as a simple perceptron. And mathematically, our generalization was simply, starting at I is equal to 1 all the way to n number of inputs, we simply grab that particular input value, multiply it by some weight that later on we'll be adjusting, plus a bias value. Later on, we're actually going to see how we can expand this model to have x be a tensor of information, where a tensor is an n-dimensional matrix. We'll also see later on that we can actually simplify this equation so that the bias is actually pulled out of the summation. So instead of having a bias 1, bias 2, bias 3, all the way to bias n, we know that there's going to be some bias b that is equal to the sum of all those. Because notice here, the bias isn't actually multiplied by the input or by the weight. So to put this in perspective, we can see here that we have a bunch of biases that are just summed on top of the input x times the weight for x1, w1, x2 times w2, and so on. So you have b1, b2, b3, b4, all the way to bn. So what I could do is I could just replace all of those, because I know theoretically for any number of biases, there exists a bias that is just the sum of all those. So I just swap that out, essentially pull it out for some general bias b that's going into that node. And as we expand this to be a layer of a bunch of nodes or a bunch of perceptrons, we'll see that the way TensorFlow thinks about things is just a single bias going into that layer. But keep in mind that, again, this bias could technically be equal to bias for 1, bias for 2, and so on, all the way to a bias n. It's just mathematically simpler to just think of some bias that's going to be the same as the sum for all those inputs. And in general, it's going to make our mathematics and equations a lot easier, and still technically everything is correct here. There does exist some bias, and we can just think of it as another input into that perceptron rather than having to add it to every single input multiplied by every single weight. So let's review what we've learned so far. We understand the very basics of a biological neuron, the fact that there's dendrites providing input to a nucleus, and then some axon as a single output. And what we've been able to do is take the research done in the late 1950s of the simple perceptron model and create a very simple mathematical model replicating those core concepts behind a neuron, where we have inputs, we apply some sort of weight to them, as well as adding a bias term, pass them through some sort of function, and then we get out that single output. So let's go ahead and then in the next lecture learn how we can expand a single perceptron to a full neural network. And then we'll see how we can add in more complex ideas such as activation functions, cost functions, and then see how that works with a feed-forward network as well as back propagation. Okay, thanks, and I'll see you at the next lecture.